Chapter 6 is about, hey, statistics. This course is called Probability and Statistics. You could even say for engineers and scientists and actuaries. We haven't done any statistics to this point. Let's start doing some statistics now. Chapter 6 is a little strange. It starts out kind of abstract, theoretical, then gets very, very practical, you might say, working with data and making concrete graphs that are commonly used. But then all of a sudden it gets theoretical again. In class, I want to focus more on the theory to help you because that's harder. And leave a lot of the practical calculations and graphs to you to read. I'll hint at what to do, and maybe we'll do a few basic things. And we will use a spreadsheet here today. But I'm going to leave a lot of that to you. We need to start conceptually and imagine this blob to represent something called a population. Now, when you use the word population, that's got connotations of like populations of people. And it certainly could be a population of people that you're thinking about, that you're trying to study, like all adults 18 and over in the entire United States or in the entire world or in Minnesota, whatever. And you want to know something about the population. Maybe just students here at Bethel University. I might wonder, what's the average height of every student here at Bethel? So my population would be to study all students at Bethel and figure out the average height. If I was going to do that, well, if I was going to do that by actually measuring people, that would be a lot of work, right? Everybody come to Dr. Kinney's office so he can measure your height. They'll also be prone to error. I'd be getting really sleepy measuring so many people's heights. And I probably would be sloppy and measure heights wrong, leading to faulty data and that kind of thing. Better, for time's sake and for not falling asleep, to study this population by studying a sample. Ideally, a random sample. So the population certainly could be people, and the random sample could be some subset of that group of people chosen at random. That's the way most people think about this kind of thing. However, remember I said at the beginning of chapter 6, it gets pretty abstract. When the textbook talks about the populations and samples, they're thinking more abstractly in terms of random variables. Being a more advanced prob and stats course and not a business stats course, you need to be able to think more abstractly in terms of random variables as well. You're already used to doing that, though, in chapters 3, 4, and 5. The population for us is going to essentially be a distribution, you could say. A possibly unknown distribution. What do I mean when I say that? I essentially mean there's a random variable you're studying. And it's got a certain distribution, meaning if it's discrete, it's got a certain probability mass function, PMF, and a certain cumulative distribution function, CDF, and you find probabilities by plugging numbers into the probability mass function. And you can find expected values and the variance and so forth. And if it's continuous, it's got a certain probability density function, PDF. And of course, then a certain cumulative distribution function that you'd find by doing integrals. And a certain mean, a certain variance, certain standard deviation. It's very possible, you might even say most common, that you don't know what the distribution is. Because you just haven't studied it enough. You haven't studied this population enough to know. Or maybe more accurately, it's impossible to know exactly what the distribution is. Nobody but God knows it. But maybe we can approximate it using data, using samples. Maybe we could hypothesize it's got a certain distribution, like maybe a normal distribution is the most common example. And if we hypothesize that, if we assume it's got a normal distribution, based on that assumption, we can figure out things about it, like its mean and standard deviation, approximately, based on a random sample. For us, a random sample is a finite list of random variables, x1, x2 through xn, that are assumed to be independent in the abstract. This is a list of independent random variables whose distribution is the same as the population distribution. It's the independence assumption that justifies calling this a random sample. These, intuitively, we're saying these random variables are unrelated to each other in the sense that if you know the value of one of them, it doesn't tell you what the value of the next one's going to be, the observed values. They do still all have the same distribution. They have the same distribution. You could even, in a sense, call them the same random variable. However, we distinguish them by calling them independent. And when we gather a numerical random sample, when we observe values of these things, knowledge of the value of, say, x1 doesn't tell you much about the value of x2, other than the fact that they come from the same distribution. Again, a common example is to assume the population has a normal distribution with a certain mean and a certain variance. And that would mean all these x's have the same, are also normal with the same mean and same variance. So we are thinking about it more abstractly than you would in a business stats course. In business stats, yeah, we do talk about random variables, but when we talk about populations and samples, we are more literally thinking in terms of like populations of people and a sample of people, or maybe populations of companies and a sample of companies, or maybe population of some product, like what? All the hammers that have been made in the last year in the entire country, and you take a random sample of actual hammers. Okay, we are thinking more concretely, and we still could do that in here. I could still use those words in that way. But because we are a more advanced prob and stats course, we want to be able to handle thinking about these more abstractly and do mathematical things with these things. And that's why we think of them this way. The population for us is a distribution, a possibly unknown probability distribution. Meaning, really, a random variable that we're studying. When I say it's about a distribution, and we're really saying it's about a random variable. And the random sample is not really numbers, it's a list of random variables that have the same distribution and are assumed to be independent of each other. It's an assumption we make to do the theory. How do you apply the theory in real life? If you gather data, statistical data in real life, like measuring people's heights and writing those numbers down and averaging them, you are gathering data about observed values. And if you pick the people at random, then they're observed values for the random sample. You don't want to pick people in a biased way, right? I would not want to just pick people on the basketball teams. That'd be a bad idea, right? That's a biased sample, not a random sample. In the old days, we used to use the metaphor of putting people's names in a hat and shaking the hat up and picking it, close your eyes, pick a name out. Oh, okay. David is going to be one person that I measure the height of. So you play basketball? No, okay. But you're fairly tall, so. But then the next person I might pick might be shorter. Okay. But now we can also talk in terms of computers and using random number generators on computers to pick random samples. Next important concept is the idea of a statistic. Emphasis also on the indefinite article there, a or a statistic or a statistic. I said I called chapter 6 about statistics. Most people, when you use the word statistics, they think about numbers and averages and graphs, maybe sports statistics. When I say a statistic, I'm referring to something more abstract in this course. A function of a random sample. In the abstract, say capital H of capital X1, comma, capital X2 through capital Xn. By the way, the number of random variables in a random sample is finite. And n is called the sample size. Whether we are thinking abstractly or concretely, n is still called the sample size. That's what a statistic is for us. Huh? That's weird. A function? Yeah, a function of a random sample. Like what function? Here's the most common one. Most common example. H of capital X1, comma, capital X2 through comma, capital Xn is, okay, let's be a little funny about it. 1 over n times x1 plus 1 over n times x2 plus ... plus 1 over n times xn. More typically written, x1 plus x2 plus ... plus xn all over n. Notice I'm using capital X's here, by the way. This is a function of the random sample, using capital X's for the random sample because they're random variables. What am I doing there? If you had to describe what I did there in one word, what would you say? Average. I took the average. Add them up and divide by how many there are. Usually you imagine the x's to be numbers and you'd say add up all those numbers and divide by the number that there are. But you want to be able to think about this in the abstract. Why do we need to think about this in the abstract? Just for kicks? No, because it's important. Why? If x1 through xn are all random variables, then this thing is also going to be a random variable. If these things have, say in the continuous case, PDFs, then this thing is going to have a PDF. Will it be the same PDF as these? No. Can we figure out what PDF it is? Yes. And if we can figure out what the PDF of this is, that might be useful for actual means of data. You should feel comfortable writing this with summation notation as well, either with the summation up in the top here like this, all divided by n, or if you prefer, you can put dividing by n as 1 over n in front times the summation. Either way is okay. Those are the same thing, right? Dividing by n is the same as multiplying by 1 over n. This is called the sample mean. We have used the word mean in here before for the expected value of a random variable. Is this an expected value? No, it's not. The expected value of a random variable x is a number. For any random variable x with finite mean, e of x is a number. This thing is not a number. It's a random variable. It's got a distribution. It's got a PDF, CDF. It's got a mean. It's got an expected value. That is a number, but it itself is not a number. It's a random variable. There's a special symbol we use for it. Capital X bar. Capital X bar, not lowercase x, capital X bar is the sample mean as a statistic. But wait a minute. Don't we want to think about observed values? Don't we want to work with data? Yeah, we do. And just like we've already done to this point, when we do think about observed values, we do use lowercase letters and numbers. You could ask the question, like, in a given situation, what is the probability that that capital X bar is greater than or equal to, 4.7 or something in a certain situation? What is what I meant to say. If you're going to calculate that probability, you need to know the distribution of X bar. You need to know its PDF. But I could certainly think about particular numbers like 4.7. I could also say, based on this data set, I observed a value of X bar of maybe 4.9, and I could use a lowercase x bar. This would be an observed value of capital X bar. Use lowercase. Are there other statistics that are important? Yeah, lots of other statistics besides X bar. The sample mean is the most important. Other examples of important statistics include trying to keep it simple as well. The maximum of x1 through xn, meaning the biggest. In the abstract, you don't know which one's the biggest. If you've got observed data, then you just pick out whichever one is the biggest to say that's the observed value of this maximum. The minimum, how about the sum of the x's by itself without dividing by n? Maybe that's important. Yeah, it is sometimes to just think about the sum rather than the mean. How about some of the squares of the values of the x's? These are more examples here. Or the cubes, etc. Yeah, those are important too. This one is related to finding a sample mean, X bar. This one, you might wonder if it's related to estimating a second moment for a random variable. And it might be. This one would be for like a third moment. maybe we have to divide by n as well to get those estimates. A little bit more subtly, there's also something called the sample median, which you can't really write a formula so much for as describe. When you talk about an observed sample median, capital M, you could say is the sample median. An observed value would be little m, observed sample median. And you can really only describe this very easily when you're imagining you've got data, and I'm going to show you an example with data here in a second. An observed sample median. You take your data, you put them in a list from lowest to greatest, and effectively the median, the observed value, is the middle number, if there is a middle number, or the average of the two middle numbers. Okay, let's look at some data. Got an example here. Somewhere, where'd it go? Here we go. This is data from chapter 6, number 9. It's more about an intersection problem, but it's not the exact same problem as the one we did at the first part of class. X is a random variable representing the time in minutes that a vehicle must wait to get through a traffic light at a very busy intersection. These are times in minutes. Sometimes they have to wait 3 or 4 or 5 minutes. It must be like, you know, a city intersection where there's a big backup. And the light turns green, but they don't make it through at first. So these are observed values of X, a random sample of observed values of X. Notice they're already in order from least to greatest if you go left to right here and then downward. If they were not in order from least to greatest, I'd have to reorder them. What is the median? It's the middle number, or average of the two middle numbers. Well, is there a middle number? How many data points do we have here? 4 times 1, 2, 3, 4, 5, 6, 7, 8, 9. 4 times 9 is 36 numbers. This is a random sample of size 36. N is 36. The 18th number is, well, 18 is half of 36, but that's not the middle number, because you could also argue that the 19th number is the middle number. When n is even, there are really two middle numbers. These two in this case. The average of those two middle numbers would be the median. Let's see if it works out with a spreadsheet function. If I type equals median, the average of the two middle numbers, 2 and 2.1, which would be 2.05, should be the median. Yep, 2.05. If you've got an odd number of numbers, let me just make something up. How about the first, how about the first 7 primes? 1, 2, 3, 4, 5, 6, 7. N is 7 there. It's not really a random sample anymore, but now there is a middle number. It's the one in the middle, 7. And that would be the median of that list. Seven. If they were not in order from least to greatest, you'd have to reorder them. The location of the median is n plus 1 over 2. But that's not the value of the median. It's just its location in the list. You guys can handle that. Business stats course, I have to emphasize that over and over and over again. N plus 1 over 2 does not equal the median. It's the location of the median. And if n is odd, like 7, that's a whole number. 7 plus 1 over 2 is 4. 7 is the 4th number in this list, whether you count from lowest to highest, 1, 2, 3, 4, or from highest to lowest, 1, 2, 3, 4. You're in the same spot. If n is even like 36, then this is not a whole number. 36 plus 1 over 2 is 18.5. There's not a middle number. The 18th and 19th numbers were the two middle numbers. Again, take their average to find that median. In general, the median is different than the average. The mean, in the spreadsheet, it's equals average. You're going to get a different number here. Could I say, just by looking at it, whether it's going to be bigger or smaller than the median? It's always a little bit dangerous to say just by looking at the numbers. It'd be better to look at a graph to help me guess. I mean, the biggest number, the max, 5.8, is certainly further from the median than the min is. That might tend to argue for a larger average. There's a few of those numbers that are pretty big. But it kind of seems like maybe there's more numbers, 0 to 1, than there are these really big numbers. I better not guess. Did end up being bigger, 2.31. I'm sure, unless I'm unlucky, the average of these numbers is also different from the median, 8.286. You may have heard, if you've learned a little stats before, that the mean is sensitive to outliers. If I make this 5.8 a 58, it greatly affects the mean, but will not affect the median. Watch. Ready? 1, 2, 3, go. Okay. Yes. Let's make it 580 to make it even more extreme. Yeah, the mean definitely got affected a lot by that outlier, but the median didn't change because I only changed the maximum value, not the middle numbers. Same kind of thing will happen down here if I make this 1700 or, oh sure, 17,000. The mean is greatly affected, but not the median. A quick plot you can make to help you guess the relative sizes of the mean and median, it's called a stem and leaf diagram, sometimes just called stem plot. To tell you the truth, I forgot what our book calls it. And the way you'd make a stem and leaf diagram with this data set, the most natural thing to do is to pick the whole number part to be the stems, 0, 1, 2, 3, 4, or 5. And pick the decimal parts to be the leaves. The leaves are attached to the stems. So the first decimal is 0.2, put a 2. The next one is 0.5, put a 5. The next one is 0.7, put a 7. That's not a 257, that's a 257. And I probably should left justify it here. What I'm really doing is I'm making a graph. Doesn't look like a graph, does it? Look at the stem of 1. What are all the leaves? Look at the decimal places. I got a 1, 2 2s, then a 3, 4 4s, 1.4, 1.4, 1.4, 1.4, 2 5s, 2 6s, and a 7 and a 9. And you want to see all those. Left justify. For the 2s, I got a 2.0, 2.1, 2.1, 2.2, 3, 5, 6, 8, 9. For the 3s, 3.0, 3.0, 3.1, 3.7, 3.7. The 4s, 4.0, 4.1, 4.5. Oops. I want that 0 to show up. And the spreadsheet thinks I'm typing a number instead of text here. So I'm in Google Sheets. I'm forgetting how to change that to text. There should be a 0 in there. Oh, okay, maybe I should. Okay, let's just make it a 115. But that first one should really be a 0. It really doesn't matter what digits you use, other than just say you want them to match what you see there. And then a 1 and an 8. And what I've really got is a graph. Turn your head sideways and look at it, and you've got a graph showing you the distribution of the data and it's got a long right tail, indicating there are some relatively high outliers compared to low outliers, and that's why the mean is bigger than the median. Question?
No, I just wanted to say if you wanted to make zero shot up easily, make them all that.
Okay, maybe you do like this instead. Oh, okay, no, I should not do that. Okay, whatever. Pretend that first one is a zero there. Okay. Stem plot, stem and leaf diagram, different names for this thing, is to give you a feel for the distribution. A more official kind of picture you're going to make based on your reading is called a histogram. Is a more official kind of bar chart that this is just a quick and dirty version of. To end class today, 2 minutes, let me just hint at what's coming. One hint I already mentioned, these statistics are random variables and they have distributions that we'd like to know about. I guess the other thing I'm about to say is something I said as well. Being random variables, they have expected values. I could think about what is the expected value of X bar. Okay, here's the punchline though. The expected value of X bar, the sample mean, does equal, when you do random sampling, the population mean. The mean of the mean is the mean. And I mean it. In fact, you can Google this. I got a video that I titled that. The mean of the mean is the mean, and I mean it. About exactly this fact. And this is one of the most fundamental facts in statistics. The mean of the mean is the mean. The expected value of the sample mean is the population mean. That's called unbiased. X bar is an unbiased estimator for mu. And we need to delve into what that is all about. This actually is a little preview of chapter 7. Okay, have a good day.